Hello everyone and good evening. Welcome to the OneClass channel. My name is Fejiro and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some extra homework help or some tutoring, please check out the links in the description below. With that being said, let's kick it off with today's session. And the first question is, how to find valence electrons of transition metals? So this is a very good question here. In fact, I do recommend that we take a quick glance at the answer here where they stress the electron configuration in the form. Well, you can't see what that sign is, but transition metals typically, in order to find how many valence electrons it has, it's important to list out its electron configuration. What does that mean? Let's look at our periodic table here to be able to know what that is. So let's say we had a, let's say titanium, for example, as we want to find out the valence electrons of it. So electron configuration, we have in terms of the off-ball principle, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, and then 3d, 4d, 5d, 6d, and then we have 4f and 5f, okay? So with that being said, we have, this is here in terms of this off-ball principle. In the S shell, only 2 electrons can go there, which is just 1 orbital. So this accounts for 2 elements on the periodic table, and that's how I like to count them. Here in the P shell, there's 3 orbitals, 6 electrons in total, so that's 6 elements on the periodic table. In the D orbital, it's going to be 5 orbitals, which is 10 electrons, which is 10 elements. And in the F, which is the lanthanum and the actinium series, that will be 14. And what I mean by this 2, 6, 10, and 14 is that if you count, for example, the hydrogen and helium, that would be your only 1s row, and you would write that as 1s2. Okay, and then for the next row, you'd see that lithium beryllium, that would be your 2s2, and then from boron to neon, as you see, it'll be 2p6. But now we're trying to get all the way to titanium. So then we finish up the third row, s2, 3p6, and then you notice when we get to the fourth row, potassium, calcium, it would still be 4s2. But the difference here is that once you get to the scandium, titanium, as you can see in just off-ball principle, we've gone through here, we've gone there, we've done this, and then we finish this row as well. The next is actually 3d, because once you get into the d orbital, you're actually technically 1 orbital prior, but they're so close to each other in terms of the energy levels. That's why you have the 3d orbital so close to the 4s orbital. But for titanium, it'll be 4s2, 3d2. Now, with all this being said, technically speaking, because this is the third shell, the amount of valence electrons for this transition metal, titanium, would be here, 4s2, which is 2 valence electrons based on the superscript. Reason being is because 4 there signifies its most outer shell, the 4th shell, specifically for titanium, okay? So with that being said, that is typically what you do to find the valence electrons of transition metals. As you see, because most of them have to pass the S rows first, most transition metals will have 2, but just in case in regards to that, the trick here is to make sure that you're counting in regards to the right amount of the electron configuration, because that way then you can make sure that when you are counting them, you make adjustments based on what the specific transition metal may need. That way you can go about making sure it's the correct one. With that being said, for example, if we pick something like chromium, you would notice that because here it would have 3d4, so for chromium here it would have 3d4 instead of 3d2 because it's going to be the fourth one, and 4s2. What happens here is because it's so close to being a half completely filled orbitals of the d orbitals, one of the electrons from the 4s goes into 3d to where chromium is actually 3d5 4s1, meaning that chromium would actually technically have one valence electron. As you can see here, if I typed in orbital configuration chromium, you would have, hope I have the right, 3d9, where is it? Hope we're looking at the right one. This is, yeah, this is chromium. It would be 3d4 that it starts with. Let's see here. What is it? Interesting. Because it wouldn't be 3d9 either. I'm pretty sure that would be 3p4, 4s2. Even the 3p4. That's very weird. Electron configurations are always very tricky to manage just because it seems like everyone has a slightly different way of approaching it. But specifically for chromium, because if you wrote it in the orbital notation here, you would see that in regards to d orbital, what chromium would do, instead of having the 4, it would use that one electron from the 4s shell to fill it here. That way it could be balanced here in regards to having at least it half full for the 3d shell. So this is typically what chromium would have, meaning that chromium would most likely have one valence electron, and you typically see it like, I could probably say that one of the ions for chromium would be chromium 1, which would be written like this, or specifically chromium 1. And then if I said chromium oxide, for example, because it only gave up one electron, because that's its most outer one, we would have Cr2O. So if I typed in, hopefully, chromium oxide, Cr2O3. Oh, that's because that's chromium 3 oxide. But if we typed in chromium 1 oxide, does chromium even have? Or is it because the d orbital? And this is why transition metals are always tricky. So, in summary, I would say the best way to find transition metals in terms of valence electrons, do check out its electron configuration. For some it works, for others it doesn't, just because transition metals are quite complicated, especially when it comes to the d orbital. So I would advise, in regards to this, definitely do the electron configuration, double check to see if any changes need to be made, and that way hopefully be able to get a better glimpse of what the chromium can do. Well, transition metals in general. Now, how can I memorize the polyatomic ions? Memorize polyatomic ions. So, this is definitely a great question as well. Just give me a brief second here to check how we're doing. Awesome. Okay, so how can I memorize the polyatomic ions as their acronym? As this answer says, unfortunately, there isn't any in terms of acronyms that I at least know of to memorize them. But the one thing I would say is that, as this question says, it's really down to just practicing. The good news is, though, is that when it comes to polyatomic ions, there are those that occur frequently, and the ones I can think of are nitrates, so NO3, sulfates, SO4, phosphate, PO4, and nitrate, sulfate, and probably carbonate. CO3. Okay, so those are the most common ones. And in regards to their charge, nitrate is minus, sulfur is 2 minus, phosphate is 3 minus, and carbonate is also 2 minus. These ones are the ones that occur very frequently, so by memorizing these, it would help you a lot to navigate the other ones. Typically, you can tell by the first part of their name. That's going to be what the main, I guess, non-metal is going to be, where the oxygen is surrounded. So nitrate, for example, it's nitrogen. Okay. Sulfate, same thing here, is sulfur. Phosphate, phosphorus, and carbonate, carbon. So that is, I like to start here because memorizing these polyatomic ions and working with them helps you memorize a lot of the ones that they're based off of later on. So for example, like you'll hear things like nitrite, which is just going to be the nitrates, but you subtract 1 oxygen. Same charge and everything. So nitrite will be NO2 minus. Nitrite. And you notice that anything that ends with ite, if you can remember the base form, the 8, you just subtract an oxygen but keep everything else the same. So then sulfite will be SO3 minus. Phosphite will be PO3 minus, well, SO3 2 minus, PO3 3 minus. And carbonite, which is a thing, is CO2 2 minus. Just take note that exactly all I did was take away an oxygen, and bam, I have all the ites. Okay. The trick here is that because I'm familiar with these, it helped me break it down further into the other forms you can take. In regards to other polyatomic ions, I do have a list here, I believe. Let's see. That will help us just be able to familiarize ourselves with them. Polyatomic ions. There we go. We have things like, another one that I do see commonly is chromate and dichromate. Usually when you're doing like some color testing, I do see these ones pop up. And you can see here, even with chlorate, you can see chlorite right under it because it follows the same rule of when you take away an oxygen. It's still the same charge and everything else. It's just going to be 1 less oxygen. There are other polyatomic ions that you should be familiar with. The ones that do appear very frequently, especially when you're working with acids and bases, are ammonium, which is NH4+. This one just appears frequently. I'm only really listing these because I'm trying to emphasize the ones that you should be really familiar with because they occur frequently, especially when you're dealing with acids and bases question. And the other one, I would say exactly the same thing with dealing with acids and bases. We have hydroxide, OH minus. Okay, this one is quite common in regards to how it shows up, especially when dealing with bases. And the last one that I do see quite a bit of, especially when just working through like some questions, I see cyanide. It's easy to, I guess, forget just because it is the one that's very distinct in terms of naming from the rest of them. Because I don't think you'd be able to get carbon and nitrogen from cyanide, but that's what cyanide is. So, in order to memorize the polyatomic ions, I can't think of an acronym, but I would say start with these 4. Okay, nitrate, sulfate, phosphate, carbonate, and also familiarize yourself with these 3. Cyanide, because it's really different from the rest. Ammonium, hopefully you'll be familiar with ammonia because those NH3 and NH4+ do occur quite frequently. And hydroxide, that one, you will see it almost often in your acids and bases questions, specifically bases, because they usually work with hydroxides. Okay, so that's the best way I can break down in regards to how you can memorize the polyatomic ions. Unfortunately, there is no shorthand way in terms of just learning an acronym to get familiar with them. It just boils down more so to practice and familiarizing yourselves with them. But I will say that once you familiarize yourself with these 4 up here, getting the ites and understanding what they mean in regards to phosphide, nitrite, carbonite, all these other things, it'd be easy to navigate once you understand the root of where it came from. Okay. Now move on to question number 3. We have balance by partial equation method. So we have copper plus nitric acid equals copper nitrate plus dinitrogen oxide plus H2O. So in order to balance this out, we're going to first write out the formula. Copper plus HNO3 turns into CuNO3 plus N2O plus H2O. So with that being said, first thing you want to do, actually, because this will technically be a redox equation, you want to be able to balance out in regards to the change in the oxidation number for each one. But in order to balance it out, you have to know what's changed. So copper, because it starts out as an element, it has an oxidation number of 0. Okay, let's make it in red to make it stand out. HNO3, oxygen typically has an oxidation number of -2, and there's 3 of them, so that's -6. Hydrogen has usually +1, and because there's 1 of them, it's going to be +1. So in order for nitric acid to be neutral in total, this has to be +5 on the nitrogen. So nitrogen here is +5. Now the copper here, well, actually before we get there, we actually look at the nitrate part. Oxygen once again is -2, and it'll be -2. Whoops, sorry. There's 3 of them, so it's -6. And nitrogen, okay, in this case, because NO3 nitrate is typically 1-, which is the result of having the +5 here. So far nothing has changed, but the copper, okay, because there's +5 -6 and there's 2 of them, the difference in total is going to be not -1 but -2. So copper needs to be +2 now in order to make up for it. So now we see there's a change in the copper. Now for N2O, same thing here. Oxygen likes to be -2, and there's only 1 of them. So nitrogen has to be +2 here, and because there's 2 of them, that means each nitrogen was +1, okay? And now with H2O, oxygen is -2, -2, and there's 2 hydrogens, so it's +2, so +1. So now we look at these bottom numbers here and mark down which has changed. Copper goes from 0 to +2, that it marks a change. Hydrogen stays +1 wherever it is, oxygen stays -2 wherever it is, but nitrogen goes from +5, not to +5 that's here, but there's also a +1 that's here, okay? So now in terms of the change, we have copper, okay, turns into copper 2+, that's what it is here, plus 2 electrons that have left that copper. Nitrogen, on the other hand, has gone from nitrogen, well, some form, nitrogen 5+, plus how many electrons get to 1? That'll be 4 electrons, turns into nitrogen plus. That's what it is there, okay? But as you notice here specifically, we have N2O, okay? So that means in regards to this, because there has to at least be 2 nitrogens, so we need to double this. Just mark it a different color. 2 of the N plus in that N2O. So in reality, we have 2 of everything here, which translates to 8 electrons and 2 nitrogen 5+. Alright, and now let's try canceling the electrons. But wait, there is 4 times more electrons from the nitrogen side than the copper side. So in order to make up for it, we also have to multiply everything up here by 4. Okay, so now we have 4 copper, which goes into 4 copper 2+, plus 8 electrons there. And you'll see finally that these 2 will cancel out, leading our formula to be, if we now replace it based on what was listed up there, we have 4 copper plus, we're going to leave this blank for now because we don't know in regards to, because there's multiple places where nitrogen occurs in the products, so we don't want to list that reactant nitrogen just yet. But we can say a specific type of nitrogen does show up once at least, because the N2O contains the 2 N plus that change. So going forward, we have 4 copper turns into 4 copper NO3 2 plus N2O, and we also don't know how many H2Os we have. We just know we have this. Okay, there's 4 coppers, which is needed for the 2 nitrogens here. Okay, so now with that being said, we've technically balanced out the electrons part. But let's see how many nitrogens we have to know how many HNO3 we have. We have here 2 nitrogens, yep, and then we have 2 more times 4, so that's 8. So 2 plus 8, we need 10 nitric acids. So we have 10 HNO3, okay? And because we have that, we can now say how many of those will turn into H2O. So because we're going to base it off of just the hydrogen, because there's a lot of oxygen showing up in different places, you never want to try to guesstimate based on something that appears multiple times in the products, which is kind of why we were building based on the things that occurred only once. So because there's 10 H2O, we know we need at least 5. Because there's 10 H's, we need at least 5 H2O here. Okay? So now with all that being said, hopefully this should balance out. Let's start by actually the simplest way, counting the oxygens to see if they match. So 10 HNO3 nitric acid is 30 oxygens total. And from this NO3 formula, we have 6 times 4, that'll be 24. Okay, and then there's 1 from the N2O, and then from the 5, H2O, 5. So 24 plus 1 plus 5, that is indeed 30. So that means this right here is our balanced chemical equation based on partial equation method, which is just indicating the oxidation reduction reaction. So that's what we did first. We balanced it out, and as you can see here, we translated that 4 and that 2 nitrogens here. That's where it happened, and because of that, we were able to get the answer to this question. So with that being said, let's see here. 4 plus 10 HNO3 is equal to 4 CuNO3 plus 5 H2O plus 1 N20. So with that, this is correct. Okay. Because exactly, we were able to go through, balance out first the electrons gained and lost. They have to be even. And then we went further by then specifically balancing the rest of the equation based on the tools we were given from the prior parts. And now I'm going to question number 4. What is the instantaneous rate of reaction? And how to determine it? So I actually like this description a lot in regards to it. Here it says the instantaneous rate of reaction is defined as a change in concentration of the species per time in a specific time given. So if you think about it, it's kind of like, it's not kind of like that at all. I would say more so because if the concentration was decreasing at a constant rate, then the instantaneous rate would equal the constant rate. But typically in the world, what happens is that as more and more product is produced or reactants is lost, because there's less things to collide with each other, the reaction usually, instead of being a straight line like that, it actually kind of goes more like this, where it balances and levels off because of the fact that there's a change occurring in regards to the products and the reactants. Okay, so this is typically what we get. So in this case, the instantaneous rate will be different than just the rate of reaction, because the rate of reaction isn't constant, it's changing over time. What the instantaneous rate does is get a specific rate at a specific time. The way you do that is you need to draw a line tangent. So it intersects only at one point, but it has to be tangent to the rate of reaction. So if I drew a line that went, so we have the 1 point there, and I guess the best line would be something that goes like that, to where it only touches that point. We can use this line, the rise over run, to figure out the instantaneous rate of reaction at this specific time. So at this time, let's say this was time 5 seconds. At 5 seconds specifically, so 5 seconds, that would be the specific instantaneous rate, specific only to that 5 seconds. You couldn't say that was just going to be the same instantaneous rate if it was like 10 seconds, which is like down here. This would have a different instantaneous rate because it will have a different tangent line. So like something like goes like this. So different tangent line, which is why it would have a different rate. Okay. So with that being said, the goal here is that the instantaneous rate of reaction is the specific rate of reaction at a specific time given, and then how you determine it is by drawing a linear line tangent to your rate of reaction, but it has to intersect at one point, and that point will be, in a sense, your rate at that specific time. And then you find the slope of your linear line, and that will be your instantaneous rate. Okay, as you can see here, that's what they did. They drew a line tangent to it. They got the rise over run, and that is how they're able to find specifically their instantaneous rate at that specific time. Okay, so with that, this is correct. Now let's move on to the next question. Question number 5. Draw the Lewis structure for a sulfite ion. In an aqueous solution, the ions interact with the H+. Predict whether the H+ will attach to the S atom or the O atom of sulfite. So they do luckily give us a name for sulfite. So Lewis for SO32-, and where does H+ interact? Okay, that's what this question is asking for. So first, if for some reason they didn't give us that sulfite was SO32-, the way you figure this out is where you start with sulfate. Hopefully you would have memorized it and gotten familiar with it, because we know sulfate is SO42-. This is sulfate, okay? And then what happens is that when you go from 8 to 8, you subtract 1 oxygen. So then you have only SO32-. So everything stays the same. The sulfur, the charge, the only difference is that now you're 1 oxygen short. This is sulfite. Okay? Now with all this being said, let's draw the Lewis structure. So for this, let's go to the periodic table to figure out where on the table it is, to see how many electrons each molecule or each atom is going to be contributing. So sulfur, okay, is on the 16th column. And also, you can also figure it out through electron configuration. If you start with neon, for example, just using the shorthand notation, it'd be 3s2, 3p4, okay? And oxygen would be helium, 2s2, 2p4. By looking at the superscripts, the 2 and the 4 here for each one, and also looking that it's on the 16th column, you can actually say that sulfur and oxygens will each be contributing 6 electrons each. So in total, we have 6 from the sulfur and 6 times 3 from the oxygen. So that'll be 24 in total, plus the 2 electrons here indicated by the 2-. So we need to accommodate for 26 electrons. Okay. With that being said, draw it out. Sulfur will be in the middle because it's the only unique one in this case. I'm going to now surround it by 3 oxygens. And we have first, second, and third oxygen. And now we're going to fill out the rest of them. So oxygens currently are sharing one of its 6. So it's going to be 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. And sulfur right now is sharing 3 of the 6. So it'll be 3, 4, 5, 6. And then because of the fact that there's 2 extra electrons, let me see, here's 3 and 3. Oh, sorry, I miscounted. Because sulfur is sharing 3 of them, so it would actually be 4, 5, and 1 extra electron. And like I said, there's 2 more valence electrons that can be used, so we can just add it to some of the oxygens out here to finish their octet rule. Because sulfur is technically already full, it wouldn't need those electrons. So with that being said, there's still this 1 lone electron and 1 here. So we're actually going to form a double bond here. It's going to break the octet rule for sulfur, but at least oxygen now is comfortable. So what we have in actuality for our Lewis structure is going to be sulfur still in the middle, but here we're going to have a double bond and a single bond here and here. These oxygens are all there. It's going to be now 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and the sulfur is right there. So with this, let's actually go ahead and calculate our formal charges for each. So sulfur's formal charge is going to be, so it usually likes to have 6 electrons, well, 6 valence electrons. So we're going to subtract from the electrons it has by itself, which is only 2, plus the electrons it's sharing, which is going to be 4, and then 8, so that's 8 over 2. Oops. Yep, so 1, 2, 3, 4, 5, 6. Yep, perfect. And so that actually equals 2 plus 4, that's 6. So sulfur has formal charge of 0, which is perfect. Now the oxygen on the most left side has 6. It's sharing 4. Well, I mean, yeah, sharing 4, but has 4 by itself. So that also equals 0. And now you actually notice where the negatives will be for this formal charge, because these oxygens on the right and the top will actually be 6 minus. It has 6 to itself. It's sharing 2. So that's 6 plus 1. So that's 6 minus 7, negative 1. So we actually see here we have the negative 1 for the formal charges on these 2 oxygens here. So with that being said, the question is asking, where does a proton interact? Considering now that we've located where the formal charge will be negative, since a proton is literally just like a positive sphere, it would be attracted to the negative parts. So it would not be the sulfur that is going to bond to, is going to interact with the oxygens. Okay, so that's what's going to happen there. Molecule is going to use the oxygens to interact with the protons when put in an acidic environment, okay, in an aqueous solution. So first, they have exactly the sulfite. They counted how many electrons they had. They drew the skeletal structure, which is what I did. Then they went ahead and just put everything as oxygens having the valence electrons. But then they decided to find their formal charges, and so that the sulfur was lacking. So then what they did was they formed a double bond with one of the oxygens, so that way the sulfur wasn't stuck at a +1 formal charge, and that way the other oxygen, one of them, could actually go from a -1 to a 0. So they were able to fix that formal charge issue. And so they chose this as their final Lewis structure, which is what we have here: one double bonded oxygen and 2 single bonded oxygens. And with that being said, the protons will attach to one of the oxygens here. So it could literally be like here or like here, for example. And you will see that if you want to like sulfurous acid, which is going to be H2SO3, that would be what this looks like here. The hydrogens will be attached to the oxygens that carry the negative formal charge. So that being said, time for a quick water break as we prepare for the next question. So we have question number 6 here. We have, write the electron configuration for the following ions, okay? The electron configuration, the ions they give us are, so electron config for the following ions. We're given A, nickel 2+, B, cadmium 2+, C, zirconium 3+, and zirconium 4+, and D, it's osmium, I think, 2+, and OS 3+. Okay. So let's start with the nickel first, but first let's just write out in terms of our whole off-ball principle. We have 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, and then 3d, 4d, 5d, 6d, and then 4f, 5f. Okay, so now let's look at the periodic table. So nickel, okay, is the 28th element. So 28th element. All right. So we want to be able to cross through all the different shells so to get to the 28th element. So the first thing we'll see is that hydrogen and helium count as your 1s row. Okay, so we have the 1s completed just like that because we have now 1s2 as we're trying to make it our way all the way to nickel. Okay, so now we have 2s2 for lithium and beryllium, and then the p shells right here starting from boron to neon, row columns 13 through 18 excluding helium are where the p orbital is going to be, so it'll be 2p6. Then we have the same 3s2, followed by 3p6, and now we have 4s2 followed by 3d8. Okay, so with this being said, we have to make sure that we actually have the right elements here. So we're going to add up all the superscripts. So we have 2 plus 2 plus 6, that's 10, 12, and 18, and then plus 2, that's 20, and then 3d8, that's 28. Okay, which does match the nickel. But now in order to find the electron configuration for nickel 2+, we have to get rid of 2 electrons. Now, personally, I would actually propose to get rid of the electrons in the most outer shell, which in this case would be the highest coefficient. And in this case, we have the 4s. So I would argue that the electron configuration for nickel would be 1s2, 2s2, 2p6, 3s2, 3p6, and then just 3d8. Just so that way we remove the most valence electrons. And we'll see if we can keep this up for the rest of these metals here. I believe they're all transition metals. So cadmium, okay, is all the way here, element number 48. So for this one, we're going to now tackle with a shorthand, because hopefully now you'll be able to track down how I was able to build up to the 4s2 3d8. So for shorthand, just to be able to actually use that as well, we start with our most recent noble gas, which is krypton, okay? And then we just proceed to count again as if you were starting from scratch. So for cadmium, it's on the fifth row. So we have 5s2. But then to cross through all this d orbital to get to cadmium, it'll be 3d10. Okay? Whoops, sorry, not 3. It'll be 4d10 because you only subtract 1 from the row you're in. Okay? So that'll be it for now. So now to find out actually the specifically what would be given up for cadmium 2 plus, I still contend that it will be its most outer shell. So for cadmium, we'll have krypton, and then we'll have just 4d10. Okay. And now for zirconium. Let's see what we have here. Element number 40. Okay. So once again, we'll start with the most recent one. That's krypton. Okay. And then once that's done, we now continue on. So it'll be still 5s2. But krypton shows up. Well, it's not krypton. Zirconium shows up a lot earlier. It'll be just 4d2. So it's 5s2, 4d2. Okay. So now the question is, which one would it get rid of first? I still personally think that because 5 is the greatest coefficient, it'll get rid of this first. Whoops. It'll get rid of this first, and then, so sorry, it'll be 4d2. It'll get rid of this first, and then it'll subtract 1 from the zirconium. And then if that doesn't work for the 4 plus, it'll just get rid of all of these. So for this, I have, it's going to be 5s2, 4d2. But because we want the zirconium, it would actually just be 4d1. Okay, that's what's going to happen here for that electron configuration when it's zirconium 3 plus. For zirconium 4 plus, it would just be this as its shorthand. Okay, so far that's A, B, and C. And now for D, we have osmium seams, which is element number 76. So first we'll do the shorthand. So xenon will be our most recent element. So we have xenon, and then we have 6s2 still. But we, as you notice, we actually passed through the lanthanum series. So with that being said, we actually have a 4f14 here. Because that's the only for you to get out and get back to what this was. And now we have 1, 2, 3, 4, 5, 6. So then for the osmium to land there exactly, we need 76, 6, 5, D6, I believe exactly. Okay, cool. So now we have this. It's OS2 plus and OS3 plus. So for this, I will once again contend that we have our most outer shell, which is going to be this. Okay. And then OS3 plus will be 5D5. Whoops. Sorry, wrong outer shell. This will be our outer shell. And then we get 5D5 for the OS3 plus. At least that's my theory. We will have, this is shorthand, 4F14, 5D6 still, which is good. And then for the one of the OS3 plus, we have same thing here, 4F14, and then 4D6. Oops, sorry. 5D5. Sorry, I was just decreasing the wrong part. But exactly, see? That way, I was now able to account for all the electrons that may have gone based on the ion given. So, even if we were to count, so xenon, as we did the shorthand, is the, sorry, let's see here, 54th element. So 54 plus 2 plus 14. So that's 54 plus 14. That would actually equal to 68 plus 2. That's 70, and then plus 6, 76. And you'll see the 76 element is indeed osmium. So this is what we would have for this question in terms of the electron configuration. Let's see how we did. So nickel, we got rid of the right one. We have, sorry, I think I put 4D10 there. It should only be, oh no, that's correct. For nickel, we have this here, 3D8, which is really good, 4S0. For cadmium, we have 4D10. Don't know why I didn't. I'm just making sure. Cadmium. I should have. Oh, it's 48. So I don't think I put. Oh, there it is. I was looking at the wrong answer. So 4D10 indeed, which is what they got for cadmium. Then ZR3 and ZR4. That's where we have this. I believe this one's a little more complicated because what I did here, I kept the d orbital and decrease the s orbital, but at least the 4 plus, both of ours are the same, but that's only because of the fact that they got rid of, in terms of zirconium where it is here, they got rid of both the d orbital, which is the 2 there, and the 5s orbital, which is the other 2, hence how we could just get this as the next answer. In regards to why they kept their S instead of their D orbital, which is a 4D1, that one's a little bit of a mystery. And you can see here, these ones are the same thing as well. It's where they keep keeping the S orbital and getting rid of the D orbital. So I would say that the D orbital, in my opinion, would be the one that makes the most sense to keep, considering that they are closer to the nucleus. And even though there is electron shielding, there's a lot more shielding that happens in the outer layer, which is why I think it would rather shed that one first. But nonetheless, we do have a little bit of conflicting answers. I probably said this is correct though, just because overall they understand the concept. It's just more so making sure that you subtract correctly when trying to decide what your new electron configuration will be. So let's move on now to question number 7. We have this about acids and bases. So with this, they're giving some information. Okay, they have the acid H2CO3. The Ka value is 4.2 times 10 to the negative 7, and the conjugate base for that is HCO3, and the Kb value for that is 2.4 times 10 to the negative 8. And then HCO3, we have 4.8 times 10 to the negative 11. That's a Ka value. And then for the conjugate base, its Kb is 2.1 times 10 to the negative 4. Okay. As you probably notice, you see that in the Ka side, the reason why it's decreasing is because once you go from H2CO3 to HCO3 minus, you've already given up one proton. So it's a little bit hard to give up the second proton. Okay. So with that being said, it says prepare a carbonate buffer at pH of 10.35. We're giving carbonic acid at H2CO3, sodium hydrogen carbonate, and sodium carbonates. Okay, and they gave us a formula. Use the information in the chart to say which species you will use. So with this, in regards to the species being used, we actually can find out which one to use by finding out the pKa of which one. Now, in regards to this, when we look for the pKa, because in regards to the pKa, it's crucial specifically here, and you can only use pKa for Ka values, not the Kb values. And pKa, okay, is equal to negative log of Ka. And the way we do this is by first getting that Ka value, the one of H2CO3, 4.2 times 10 to the negative 7. Okay, so that'd be 4.2 times 10 to the negative 7. And then we use that, so this negative log that, and we get 6.376. In regards to choose a correct buffer, we want the pKa to be at least relatively close to the pH given. So with that being said, let's try checking out the other one, because this one is quite far. So we have 4.8 times 10 to the negative 11. And then when we go through that, the pKa becomes 10.31. So with that being said, the HCO3 is the one that's going to take the lead, because that one doesn't let me see exactly. Now we're going to use the HCO3 because that one's a lot closer to the pH, the buffer pH we're actually trying to solve for. So with that being said, so pKa of HCO3 minus, okay, is equal to pKa of HCO3 is equal to 10.32. Okay, that's already quite close to 10.35, which is why when it asks the question of using information, which one would you use, I would say HCO3 plus CO2. HCO3 and then CO3 2 minus. So it's minus 2 minus. That is the buffer solution I'm going to pick here, HCO3 and CO3 2 minus, because the pKa is so close to what we're looking for in regards to the pH. Now, which component we present in the larger amount? So for this, actually, we have to use ratios, and so we'll see that in regards to the larger amount of what we would need, we actually use this formula here. It would be pH is equal to negative, oops, sorry, not negative, bad habits. pH is equal to, let me just think here in regards to Ka. We have pKa plus log over log. Okay. So now what we can do is, in a sense, find out specifically which component will have a larger amount. So with that being said, just to make sure, we have pH of 10.35, which is what we wanted, is equal to pKa. So pKa here is 10.32 plus plus the logs of each one. So now in order to get rid of this log, sorry, it's not even a log, I don't know why I did that, it's pKa plus conjugate base over conjugate acid. There we go, no wonder. Conjugate base over conjugate acid. Okay. So now we have that if we subtracted 0.03, that is between, so 0.03 inches is the difference between the concentration of base or the concentration of HA. Okay. pH equals to pKa plus that. So that would be that. And then we have this left. We want that pH. pKa plus that. So with this, actually, it's just the component present in the larger amount. Just trying to make sure that I have this math correct. pkh equals pka. Subtract 0.003 is equal to a over ha. That means which one? pH equals to pKa plus that plus hope I use the right numbers. Okay. A over HA equals 0.03. Okay, so which component will be present in the larger amount? For this one, this is, I would say, this is more of a conceptual question, because in regards to the larger amount, we have 10.35. Why is that doing that though? pH equals to pKa plus a over HA. Let's see what they did here. Yep, they did that. Log. No wonder I was missing a log. Log. There we go. And that means exactly. So then when we do 10 to the power of, logs cancel out. So it'll be 10 to the power of 0.03 is equal to a minus over HA. So in this one, we're missing the logarithmic part. So here, as you can see, equals that. And so with that being said, 10 to the power of 0.03, well, to be more specific, 10.35 minus that answer. So then now we have 10 to the power of that, 1.07. There we go. Okay, so now we have 1.07 relation between a minus over HA. And with that being said, that means that if we did 1.07 over 1, we have 1.07 times more base than acid. Okay, so that's what we have there. All right, so now we want to be able to apply this into the last part, which, so that we have this so far. We want to use this, so we've answered 2 of the questions. The last question to ask is, we're given a 0.025 solution of the acid and 0.025 solution of the base. Now the question is asking specifically how do we calculate the mils of each one we would use to make the buffer. Well, with that being said, we would need to first establish the ratio. We have 1.07 to 1 of A minus over HA. And so with this, what we can do is you have to add 0.25 moles of each. We need to understand the mils. To solve for this, we would then cross multiply first to be able to get A minus is equal to 1.07 HA. Alright, and if we're gotten 0.025 moles of each, we have 0.025 is equal to 1.07 times 0.025, which isn't the case. It's just like them equaling each other, but we're trying to now convert this in terms of mils. But for this to work, we have to make a very big assumption here. Is let's say we're using we want a total of 1 liter, for example. That's a pretty good amount. So times 0.025. So right now we have 0.025 and we have 0.0268. Okay. And now, with that being said, let's see here, just to make sure we have this correctly. we're going to convert this to mils, and to convert it to mils, we need to base it off of the molar mass, because moles per liter is equal to, no, we don't need molar mass. Moles per liter is equal to moles per liter is equal to, don't know why I'm blanking on the word, but I will get the word briefly. In regards to this, what we need to do now is there we go. Now that we have this ratio here, we need to now establish this again. So we have 0.0268, so this will be crossed out, is equal to x over x, well, sorry, because we want to, let's say we want to have 1 liter in total, so we're going to have 0.5 here over 0.5 plus x. That's what we're going to use here to be able to establish this, because we want to be able to get this ratio here. So 0.25 divided by that, what we just got, oops, sorry, there we go, so that's like 0.93 is equal to 0.5 over 0.5 plus x, because we know that each of them has to be able to add in total to 1 mil. So right now I'm saying half, not 1 mil, 1 liter, so I'm saying half a liter for both, but we need to be able to make up for the fact that this one has more. So sorry, actually minus x and plus x, because we're going to be offsetting the balance there. So with that being said, so 0.93, multiply that by the 0.5, so that's 0.46 plus 0.93x is equal to 0.5 minus x. So now we're going to now isolate to one end, so then minus 0.93 from both, whoops, we're going to plus the x on both sides. Okay, so this is crossed out, and then we're going to subtract the 0.46 minus the 0.5, and 0.93 plus x is 1.93x is equal to 0.0347, and so if we divide this by 1.93, so let me just make sure, 0.46, 0.93x, so divided by 1.93, we get x is equal to 0.017, or 18 specifically. That is going to be the difference in change. So that means in order for it to now work in the solution, we would need 0.5 minus that much. Okay, so one of them needs 0.482 mils, and we established that's going to be the acid, because we're going to need more base. So 0.482 liters of acid, and then for the base we're going to need plus 5 plus answer. So 0.5 plus that change, it will be 0.518 liters of the, so this is the acid, it would be HA, this would be the A minus, and you'll see when you add those two together, you should get 1, because that's going to be a total of 1 liter. So this here, when we do that, this is going to give us a pH of 10.35 buffer solution. Okay, so that one's a little bit more complicated in terms of how to figure that out, but you just have to make sure first that you know what you're solving for based on the fact that we established this relationship here. Okay, so exactly, they got this, and so the difference is 0.03, 1.07, so that means CO3, the base, is 1.07 times more than the acid. So CO3 is a larger amount, so perfect, that's what we wanted. And then using that equation, they're able to now break it apart into this equation here. So in the volume, what they did was a little bit different. They had what they had was although our numbers are quite close because they rounded, that's why, because we got 44.82. What they had was that they wanted just 100 mil. We have a whole liter here, which is why we have 4.82. But overall, exactly, because they rounded to 1.07, while I kept with the actual accurate numbers. But as you can see, numbers aren't too far off. I got 0.518, which is similar to their 5169, and they got 48.31 mils, which is close to our 0.482 liters. So this is correct. The important thing is that the last part what they did was just, in a sense, assume that they had 100 mil, while for me I assumed that there was 1 liter. So question 8 here, it asks, a person suffering from from hyponatremia has which of following? So for this one, I'm not gonna list on the answer as you can see there, but this will be more of a conceptual question. I know you may be able to see the answer down there, but the options they give us are too much sodium in the bloodstream, too little sodium in the bloodstream, equal concentrations of water and sodium, and too little water. So for this, right away we'd actually cross out C. It's not C because if you remember your prefixes, hypo means less, hyper means more, and iso, okay, especially when you're talking about osmosis and the solutions, we have a hypotonic, hypertonic, and isotonic. And isotonic, so iso, that prefix, it would mean same. So with that, because it's hypo, we know we cannot have equal concentrations of water and sodium in the bloodstream. That won't be incorrect, okay? So now it goes down to which one we'd like to choose. Hypotonic means too little of something. So in order for us to be able to tackle this question better, I would say we'd cross out the answers that also don't say too little. So A as well cannot be a choice because it says too much sodium in the bloodstream. So now it's between too little sodium and too little water. Here is a part that needs a little bit more of an in-depth thinking here, because although I am familiar with the word, this is more for you to be able to make a proper educated guess in regards to this, just because sometimes you'll see this and you're not given an option to search it up. Here, what I'm going to say is that specifically when you're talking about solutions, what I've noticed is that they always refer, whether it's tonic or natremia or other types of hypo and hyper that you might see, usually are referring to the solute in it, not the solvent. And water is typically always the solvent. So with that being said, when you even think of a hypotonic solution, it's saying that compared to another solution, this solution here is less concentrated. So it's referring to the solutes in that solution. Hypertonic is usually referring again to the solutes there, but it's going to be more concentrated in a different solution, okay? And iso would be equal concentrations of both. So with this, because water is typically treated as a solvent, okay, I would actually stray away from D because it's referring to too little water in the bloodstream. And because it's a solvent, typically you won't see hypo, hyper, and all these different types of words refer to the solvent. So the only option here actually will be too little sodium. And the reason why I picked that is because of the fact that that is the only one referring to the possible solute there, and it's also abiding by the hypo, which would be little or less. So with this, B would be the correct answer I would pick. And as you can see here, when they actually search it up and read it, it says a hyponatremia is a condition that occurs when the level of sodium in the blood is too low. When that happens, the body's holding on to too much water, but we don't say that it's a condition set up by too much water. It's a condition set up by too little sodium, and because of that, the bloodstream is very diluted, kind of like hypotonic, where the solution is less concentrated. And because there's less concentration, you'll see that the water is a lot more, I guess watery would be the word to use, or just not as viscous or thick, which you don't want your blood to be either, but pretty much it'll be too thin. Your blood will be too thin to where it kind of just, let's say you get a cut, for example, it would be harder for it to, I guess, stop bleeding, because it's almost like water pouring out in more extreme cases. But exactly, this, in this case here, it's not because the water is too much, it's because the sodium is too little, making the concentration very low. Okay? Now let's move on to question number 9. Is water boiling an example of chemical change? So, water boiling, chemical. So with this question, I'm just going to say the answer right now is no, just because as long as we're assuming that it's not like the water that's touching the surface of like the pot, for example. If you're just trying to like boil water, the bubbles produced, that is technically, you could say it's a chemical change, because what's happening there is probably like some form of redox reaction, to where the water molecules, because as soon as they touch the surface of the pot, which is why when you notice it and you see things boiling, you can see the bubbles that start from the bottom and then they go up. Okay, that's because the metal surface allows the redox reaction to occur, where you're having the H2O, or typically like 2H2O specifically, it'll break into the 2H2 plus O2. Okay, but this can't really just occur by itself. You need a condition to be met for it to do that. You can definitely heat up water, which is what water boiling is. It doesn't have to be with the bubbles. It's just that as you get to a certain temperature, with enough energy, you're able to now have these reactions occur. Okay, but this reaction here, this is chemical. Reason why? Because chemical versus physical changes are when only intermolecular forces are broken, so you don't see bonds being broken. But in chemical, bonds are broken. So you have H2O here, okay, and the only way for it to get to 2H2, these bonds had to be broken, and that is a chemical change right there. So in this question, there is a chance of a chemical reaction happening while the water is boiling. But let's say you were heating it in a microwave, for example. That is still raising the temperature of the water. It's always tricky because there's a difference, I guess, between water vapor and this. Okay, this right here is a chemical change. Water vapor, on the other hand, so after a while you see that there's no bubbles, right? But you've boiled your water and you see steam keep coming out of it. Okay, there's no bubbles anymore. That it's kind of like the pot's now relaxed, cooling down a bit, but the water itself is hot. This steam right here, this is a physical change, because it's now transitioning. It's being boiled. The boiling its boiling temperature is like 100 degrees, so it's being changed from a liquid state to a gaseous state. And that isn't a breaking of the water molecules, more so the intermolecular forces that kind of help the water molecules stay close to each other. So for example, the hydrogen bond here, with enough heat, you can break this hydrogen bond to where now the water molecules can now drift apart from each other. Hence what this steam is, and that would be a physical change. So to recap, is water boiling itself example of chemical change? No. But can you note chemical changes in there? Like this, for example? Yes. Okay. Like I said, that one will be when you see the bubbles at the bottom and they float to the top. That would be typically this reaction seen here. If you're kind of just seeing like a hot cup of water and there's steam above it, that wouldn't be this here. It would be a physical change of water just changing states. Okay. So with that being said, let's see how we did. They do mention that the bubbles were caused by decomposition of molecules into gas. This is what we have here, the 2H2 plus O2. That would be an example of a chemical change, but the boiling water itself is an example of physical change because the water vapor still has a molecular structure as physical water, well, as liquid water. So this is correct. So now question number 10. What volume of ethanol must be poured into a graduated cylinder to obtain 30.3 grams of ethanol? It has a density of 0.789 grams per centimeters cubed. So right now we're giving density, okay? So we have, so it says 30.3 grams of ethanol and density of 0.789 grams per centimeter cubed. Okay, and we're trying to use this to be able to find the specifically the well, that's a tricky one. We were given the mass, and then we were given the grams per centimeter cubed. So then for this one, we almost have to assume that centimeters cubed can be transferred to 1 mil. We may have to make that assumption. Let's see how we can do this. So first we have, as they showed there, density is equal to mass over volume, okay, which is what's given here, and we're given the mass. So if we arrange it, we actually have to find volume. It'd be volume is equal to mass over density, just as we rearranged it. So we have volume is equal to 30.3 grams over, well, yeah, over 0.789 grams, so these two cancel out, per centimeter, which allows it to move up here. The centimeters cubed moves to the numerator because it's being divided in the denominator, so that's why it shifts up there, and that'll be our only unit. So in regards to that, now we have 30.3 divided by 0.789, so that'll be 38.4. If we're going to round the same way, centimeter cubed for the volume. Now, if the assumption was, which is key, assume 1 mil is equal to 1 mil is equal to 1 centimeter cubed, we can then say our answer is 38.4 mil. Yes, 1 mil is equal to 1 centimeter cubed. Although, or is it 1 mil is equal to 1 milliliter cubed? I'm pretty sure that would be the conversion there. I may be wrong, but that's what I would do there. Let's see our units of conversion to double check. Okay, 1 liter, okay, is equal to 0.01 meters or 1,000 centimeters cubed. So 1 millimeter is equal to 1 centimeter cubed. Perfect. And now let's see how we did then based on this assumption. So exactly, they make the same assumption here and they're able to say, yep, 38.4 mils. So 38.4 mils of ethanol is required to obtain 30.3 grams of ethanol based on the density given, and we're able to rearrange the formula to where we're looking for volume now. Okay, so that being said, this is correct. And now question number 11. Given the following acids and the Ka values. Which is the order of increasing base strength? And I emphasize base because that's not acid. We're looking for the order of base strength, okay? So, now, with that being said, they were giving us HClO4, HOAC, HCN, and HF, and these ones had 3.53 times 10 to the negative 4, 4.93 times 10 to the negative 10, 1.76 times 10 to the negative 5, and 1 times 10 to the 7. Wow, okay, definitely blows them all out the water. So, let's first ignore the question briefly and just understand what the Ka values mean, okay? So for this, a higher Ka value means a stronger acid, okay? So, if you wanted to label this by strongest to weakest acid, we have the biggest number of the Ka will be here, then it will be the HF, then HOAC, and HCN. We've now gone through and labeled these all by the acid strength, okay? So HCl4 being the strongest acid. But now, if we're going by base strength, if you're a strong acid, you're either not a base or a very weak base. So you'd be like the lowest base strength, okay? So with that being said, if we were to organize this now by the strongest base, it would be the lowest acid. So it would be 1, 2, 3, 4. Because HCl4 is such a strong acid, it would be the weakest base. But now they're asking for us, now we look at the question finally, increasing base strength. So we want to start from the weakest to the strongest, okay? So if we list it out, we would go 4, 3, 2, 1. So it would be HClO4 would be the lowest, then it increases to HF, then it increases to HOAC, then finally the last one is HCN. This should be the order we're looking for based on our order and based on what the Ka values mean. So that being said, let's see what we're dealing with, okay? So as you notice right away when we look at the answers, they don't have the protons anymore, the hydrogens, which is actually the more accurate choice because of the fact that we're looking for the increasing base strength, you're looking at the conjugate base. So right under here, I'll actually write down what the conjugate base for each one would be. That'll be without the protons. So ClO4 minus, OAC minus, CN minus, and F minus. Okay, that would be it. So with that being said, we would actually have OAC and that. This would be all our conjugate bases in the order. So with that being said, we have ClO4, F, OAC, and CN. And the only answer that matches that completely would be C. C would be the order of increasing base strength because at the end, cyanide is the strongest one and the weakest base, in fact, probably not even act as a base at all, would be ClO4 minus. Because of, as a side note, when you see a Ka value that's greater than 1, as that 1 times 10 to the 7, that means that it literally dissociates completely. It wants nothing to do with that proton. So in fact, if you put ClO4 in a heavily acidic environment, it won't take any hydrogens to itself. It will literally just sit there as ClO4 minus. Cyanide, on the other hand, throw it into an acidic environment and you will definitely see some HCNs floating about. That's what would happen there. So exactly, so weakest base, and it will increase there to the strongest base right here. Okay, and that is what our answer is going to be, C. So ClO4, F minus, OAC, and CN, because when you order it, it's going to be the strongest acid to the weakest acid, which is what they did. And if you're the strongest acid, that means you're going to be the weakest base, or even not a base at all. So let's move on now to question number 12. Let's just quickly see how we're doing here. Awesome. Okay. What is the conjugate acid of hydrosulfuric? Well, HSO4 minus. So conjugate acid of HSO4 minus. So with that being said, if we want to find out the conjugate acid, we have to assume that it's reacting with that this will be the base. So we have this base here. So if we want a base, we want to be able to make it react with water. So we have HSO4 minus plus H2O. Okay. Reason why I write it like this, because right now it's asking for the conjugate acid. So this is our base. This is our acid in this case. So then, because that's due to the rules of the Bronsted-Lowry acid and bases, hydrogen is going to donate a proton to HSO4. So we're going to have H2SO4, no longer minus here. So this will be our conjugate acid, plus OH minus will be our conjugate base for water. So as this question asks, the conjugate acid of HSO4 will be H2SO4. So the answer should be sulfuric acid. And this here, the HSO4, that one, if you're curious about its name, would be a hydrogen sulfate ion, I believe. So with that being said, the conjugate acid will be sulfuric acid H2SO4. Okay, and it's only asking for the conjugate acid. If the question asks for the conjugate base, for example, it'd be HSO4 again, but this time I would actually use OH, because now this is acting as the acid, this will be acting as a base, and then we would get SO4 2 minus, so it would be a sulfate ion, which is going to be the conjugate base, plus H2O, which would be the conjugate acid here. And you can see they still match, and SO4 2 minus would be the conjugate base. Okay, so that would be how you do the conjugate acid of HSO4. It's important that you note what they're asking for instead of whether it's acid or base, because the conjugate acid will have one more proton, and the conjugate base will have one less proton. Okay, so with that being said, this is correct. And now question number 13. Okay, let me just double check here. Alright, let's see. Still good to go. And let's see. What is a conjugate acid and base pair? Wow, fitting. Conjugate acid and base pair. So what this question is asking for is, how do you identify what the conjugate acid and base pair is? The key difference here is that there has to be one proton difference. Okay, so for example, if I gave you H2SO4 and HCO3 minus, yes, the CO3 minus has one less, the HCO3 minus has one proton difference, but you can see here that there's one that's the sulfate ion and one that's a carbonate ion. Those are two different structures, really, they won't be the conjugate acid and base pair of each other. What you would be looking for here would be HSO4 minus and H2CO3 right here. Those would be each other's conjugate acid and base pair. The key thing is that there's one oxygen difference. Another example would be H2O and OH minus. Okay, these are conjugate acid base pairs. Now in regards to telling me which one the conjugate acid and the base is, the one with the extra proton is the acid, the one with the less proton is the base. So this would be the conjugate acid here, this would be the base here. Okay, and another example, if I gave you this H3O plus and OH minus, these are not conjugate acid base pairs of each other, because now the difference between them isn't one but two hydrogens. So in reality, the conjugate acid base pair for this, both of them will be water, but that's because the intermediary step. So if I actually did this, H2O like that, between here, okay, this would be the conjugate acid, conjugate base, and here this would be the conjugate acid, and that would be the conjugate base, like I said above. But exactly these two here would not be conjugate acid base pairs of each other, because there's more than one proton difference. Okay, so that's a key thing. Difference by the presence and absence of one proton is a conjugate acid base pair. For example, they give the example of ammonia versus ammonium. This is a conjugate acid because one more extra proton, and when ammonia is a base because it's one less proton. So this is correct. And with that, I've just stressed exactly, look for just the slight differences of just the one more proton or one less proton. That can be the only difference there. You will notice a charge change, but hopefully for the molecule itself, you can say that's the only difference there. So even if I had H2SO4 and then HSO3 minus, this is sulfuric acid, and this right here is hydrogen sulfide. You can see here the difference is that there's a 4 and a 3 oxygen. Those two will not be conjugate base pairs, even with that slight difference, because it's a different amount of oxygens. All we're looking for is that they differ in one proton, the hydrogen. So now question number 14, we have the name of this compound, okay? Name of P4O10 is, so in order for us to name this, we first have to identify what type of molecule this is, okay? Is this going to be an ionic compound or molecular compound? The way we figure this out is by going to the periodic table and seeing what phosphorus and oxygen are. So we have phosphorus and oxygen, okay? So that is all the way here. So we have phosphorus here, element 15, and oxygen here, element 8, and they're both listed based on the color coding as reactive nonmetals. So in this compound, we have no metals. So it's not an ionic compound because that needs a metal and a nonmetal. It's actually going to be a molecular compound. With that being said, it follows its own naming rules. Because it's a molecular compound, we still need phosphorus, okay? And then we need the oxygen. But here, instead of it being oxygen, we still follow the rules where we drop the ending and add the "ide," okay? That's very important. But now where it differs from ionic compound naming is you actually have to indicate how many of the atoms you have in there based on the prefixes. So for example, 10 would be deca. So this would be deca oxide, Okay, that's 10, I believe, because that's non-deca. Yeah, and then 4 is tetra. Okay, so we have tetra phosphorus deca oxide. That's the key there in terms of naming these, is that you have to make sure you account for the actual amount of, I guess, atoms you have. And we use that by remembering our naming. So we have, for example, mono, bi, tri, tetra, penta, hexa, hepta, octa, let's see, what else is there? Nona and deca. And each one of them is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 respectively. Okay, and that's how we were able to get this name here. With that being said, based on our choices, phosphorus oxide will be assuming that it was like an ionic compound, which is not. Tetraphosphorus deca oxide, that is what we want, so we can say the answer is B. As you can see here, C only accounts for the first part, but you still need to be able to identify how many of the second part you have. And D, same thing. Okay, if phosphorus was just P by itself, then you don't typically see the mono in the first one. Like for example, a good example of that, dihydrogen monoxide, where you actually have, two hydrogens and one oxide. But then when you have like a nitrogen dioxide, you rarely hear mononitrogen dioxide. You just say nitrogen dioxide. With that being said, though, phosphorus deca oxide is wrong because it ignores that it has 4 phosphorus there. So the only answer is B, tetraphosphorus deca oxide. Okay, so now let's move on to question number 15 here. What is a systematic name of MgNO3(2)? So for this, we still have to check whether it's an ionic or molecular compound. So for this, we have to go through our periodic table. We have magnesium, nitrogen, and oxygen. Okay, so look at the periodic table here. Magnesium is indeed a metal. It's an alkaline earth metal. Nitrogen and oxygen are both reactive nonmetals, as they say here. So with that being said, we have a metal and we have a non-metal component, so this is indeed an ionic compound. Okay, so with that being said, we at least have the first part. Because it's ionic, we can just say it's going to start definitely with magnesium. Alright, so we have that part done. Now, NO3, okay, that part's tricky because unfortunately it has to be memorized. NO3 is not, you wouldn't think of it as a magnesium, then it'd be nitrogen trioxide or something. That wouldn't be the case. This here, this ion is known as nitrate. How do we do this? The nitrogen, okay, that's the important part. But instead of it being, so nitrogen, instead of being the nitrogen, it drops that part. And once you start involving a certain amount of oxygen, it becomes nitrate. And for nitrate to exist, it's NO3. There's also nitrite, which is NO2. But exactly, you have to recognize that when you see a nitrogen paired with 3 oxygens, that would be nitrate. In nitrate ions, NO3 typically have a charge of just -1, which is why there's 2 here. Because magnesium has a charge as an alkaline earth metal of 2+, which is why you need 2 nitrates to be able to balance out this to make it a neutral compound. So we have magnesium nitrate. And no, because it's an ionic compound, you do not need to, in fact, you should not indicate how many nitrates you have. You wouldn't say magnesium dinitrate, it would just be magnesium nitrate. Okay? And exactly. So magnesium, it's ionic compound because it's metal, non-metal, and we just say magnesium nitrate. This is correct. And now we move on to question number 16 here. A brief water in the meantime. All right, so just to make sure that everything is good, I'm gonna do one more quick check. All right, perfect. So the audio is good, everything is good to see. Okay, let's bring it back to the lesson. We have, what is the name of N2Cl4? Name of N2Cl4. So first we have to, as they say, explain what type of bond type this is and the steps we use to name it. So first, let's go to handy periodic table. We have 2 nitrogens, so that's nitrogen, and chlorine. So the first step we have to do, just as to determine the bonds, is say what type of molecule this is, ionic versus molecular. We have nitrogen and chlorine, both of which are non-metals, okay? So there's no metals present. Because of that, we can say this is a molecular compound, okay? Well, I think the better name is covalent. Ionic versus covalent. Covalent compound, okay? So with that being said, because it's a covalent compound, it has its own naming rules, and you can actually support that further by, if you hover over nitrogen and chlorine, you'd actually see the nitrogen has electronegativity of 3.04, chlorine's electronegativity is 3.16. So in fact, you could say that it's even non-polar bonds between them because of the fact that the electronegativity difference is so small. So this is definitely a covalent compound, okay? So with that being said, okay, we have N2Cl4. To name this, we're just going to write down simply, what we have. Nitrogen, chlorine. But we're not done here. The naming rules for this is that first, we still have to go similar to the ionic compounds where we drop the N for chlorine and replace it with I. So nitrogen chloride, okay? But now here's where the biggest difference lies. When it comes to covalent compounds, you have to indicate the amount of, compounds there are based on the prefixes of, mono, di, tri, tetra, penta. This is 1, 2, 3, 4, 5 respectively. And we're just going to use this because it doesn't go past 4. So we don't need to know like the 6, 7, 8, 9, 10. But just for your reference, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. Okay? So for this, we have 4 chlorides and 2 nitrogens. Let's add a little bit of space here between them. And we want to be able to fit the tetrachloride here. Okay? And we cannot forget about the nitrogen because there's 2 of them. It would be dinitrogen. So this would be the full name for this. We changed the ending from chlorine to chloride. Then we indicated how many of each atom we had with the prefixes. So let's see how we did. N2Cl4, change the N to ide, dinitrogen tetrachloride. Perfect. And now is on to question number 17. We have, what is the molar mass of sulfuric acid? So for this, let's actually briefly pretend that we weren't given the name of it, just so that way we can kind of try to navigate what sulfuric acid is. So if we're given the name sulfuric acid, we first have to understand where it's coming from. So sulfuric acid, we know there's sulfur in there, okay? Now this is the part you have to memorize, because unfortunately when you're dealing with ic, so it has a ic acid, so it ends like that, we're dealing with typically a 8, so like sulfate, nitrate, carbonate, phosphate, but in this case it would be sulfate. So it's a sulfate ion that we're using to form it, and sulfate is SO4 2 minus. This is a sulfate ion, okay? So in order to get sulfuric acid, acid indicates that there's protons involved. You need the same amount of protons to be able to cancel out this 2 minus to make a neutral molecule. So you need 2 protons there, which is just hydrogens. So we have H2SO4. Hence how we got that, which is exactly what they're asking for. Now to find the molar mass, we have to add up the constituents. So we have 2 hydrogens, 1 sulfur, 4 oxygen, okay? And so we're going to use our periodic table to figure out how much each of them weighs, their atomic mass units. So that'd be 1.008. Sulfur is 32.06, and oxygen is 15.999. So let's multiply each one. This stays the same since it was just 1 sulfur. Hydrogen is 2.016, and oxygen would be easier done with a calculator. 15.999 times 4. That's 63.996. We're going to add all of them together, and by adding them together, you've now accounted for all your constituents of sulfuric acid, and so you'll get 0.2016 plus 32.06, 98.072 grams per mole. Okay, that is the answer you should get for the molar mass of sulfuric acid. So let's see how we did here. Added the constituents, and their answer is slightly different just because on their periodic table, as you see here, oxygen was just 16 grams per mole, but every of our other values did match. It's just important that when you do solve this, you base it out specifically on the periodic table that was given to you. You don't want to be trying to search it up to find out their atomic mass units, just because periodic tables can vary based on the information given on how they calculated each atomic mass. So to be consistent, I would always stick to the same periodic table rather than getting references from different periodic tables. Okay, so this is correct. Now let's move on to the next question. Question 18. So this question is asking for the name of the following compound. Okay, so they want NH4 2S. So for this, same thing applies. We want to see whether we're dealing with this one is a little bit tricky because this is technically a covalent compound, but because it's a specific type, we have to recognize that. So this NH4 here, you have to memorize it and recognize it as ammonium. And ammonium doesn't abide by the same rules of what when we have like a covalent compound, we have to indicate the quantity of them. So you will never see like something like diammonium. Ammonium itself works almost like metal, if that makes sense, at least with the naming. Okay, with the naming, it's the metal component, so you wouldn't need to indicate how many you have. So that's why it just stays as ammonium. Okay, so right now we have ammonium. Now this is known as sulfur. Okay, that's sulfur. But as the rule says, you don't just put sulfur down here. You need to be able to indicate how many, well, sorry, you need to be able to change the ending to where you have the IDE. So it will be ammonium sulfide, okay? So with that being said, okay, this will be, just as a review, ammonium is known as the NH4 plus, sulfide is known as the S2 minus, which is why together, I'm going to make this red just to be able to compare the metal and the non-metal parts. That's why you need two ammoniums, which is what's happening here. Two ammoniums to be able to match with a sulfide, which is how we get ammonium sulfide. So with that being said, ammonium sulfate, that wouldn't be it. Sulfate is SO4 2 minus. That's the sulfate ion. So B is looking better. Hydronium would be H3O plus. That's hydronium. And D, no correct response. We can't use that because indeed our answer is found in B. B is our correct answer. So exactly, they try to follow the rules for naming molecular compounds. So, but in this case, because ammonium follows its own rules, you can't really use that because you will see that you want to be able to include the mono, di, and everything else, but you would not do that for ammonium. So with that being said, ammonium sulfide is the answer. You would not see diammonium sulfide ever, because this is one of the exceptions to where it almost follows the name rules of an ionic compound, even though it's a molecular covalent compound. Okay. Now question number 19. Okay. What is a concentration of K plus ions in 0.025 moles, or moles per liter, molarity of K2CO3 solution, assuming complete dissociation? So what this is asking for is, first we write the formula. So we have K2CO3, that is potassium carbonate, and we're assuming complete dissociation, so we have now potassium floating around plus carbonate. But you have to notice it's K2CO3, so we have 2K plus CO3. So if we now had a starting concentration of 0.025 molarity here, to be able to now convert, we would just kind of solve it as we're doing any conversion question. 0.025 moles, or moles per liter of K2CO3. Okay, and you can see here, based on this formula, 1 molarity of K2CO3 is equal to 2 molarities of K plus. So now we can cancel these out, and it's going to be 0.025 times 2. So we're going to have 0.050 molarity of K plus. This would be the concentration of K plus ions, assuming complete dissociation, the 1:2 ratio that we see in the formula. So as you see here, they did that. They have the 1:2 ratio. That's how they got 0.050 molarity. And this is correct. Awesome. So now let's see quickly how we're doing. Hopefully everything is going well. Okay. So we're still looking good here. And now we're going to tackle the last question. And that is, Let me just make sure. Sorry. There we go. Question 20 is going to be, ooh, this is a good one. Carbon disulfide, so CaS2, is prepared by heating sulfur and charcoal, and the chemical equation is S2 gas plus carbon solid turns into CS2 gas, okay? And the Kc, which is the dissociation constant, is 9.4. Well, not this. I guess the formation slash dissociation equilibrium. There we go. The equilibrium constant. There we go. Is 9.4 at 900 K. How many grams of CS2 can be prepared? How many grams of CS2 can be prepared by heating 9.97 moles of S2 gas, 97 moles of S2 gas with excess carbon, so this excess, in a 6.5 liter reaction vessel held at 900 Kelvin, okay? So it's met its requirements. It's at 900 Kelvin, so that's perfect. So in a sense, we kind of want to see how many moles is produced to get that much gas here. Because this doesn't give us the pressure, this wouldn't be a PV equals nRT. So because they don't give us the pressure, that liters they gave us, the 6.5, can't really be used in this question. It's just saying that's the amount of space we have. If there's a pressure given, we'd be able to see maybe how many, the maximum amount of moles it could produce to be in that confined space. Because after a while, you know, you'd hit your limit to where you couldn't expand anymore. But considering that's not given, that's not something we would factor. The only thing we're looking at is specifically the amount of, moles of CS2 is going to be produced. Now, at first glance, you may think that you can just put 9.97 because it's a 1-to-1 ratio, right? But that would be wrong, okay? Here, what you actually want to figure out is, because the Kc is 9.4, you actually have to use the products over reactants to find the equilibrium. So Kc is equal to products over reactants. It's going to be the concentration of CS2, so the moles of it, over the moles of S2, okay, times the moles of C. But because C is a solid, when you're trying to find the equilibrium, you do not factor in, which is also convenient that they have it in excess, you don't factor in the solid, okay? So let's say the Kc is 9.4, all right? So that means that in order for this to equal 9.4, it has to be something divided by, as it gave us, 9.97 moles, okay? So X. So then if we multiply these together, we have, let's see here, 9.4, 900 degrees Kelvin. We'd have to do 9.4 times, just making sure here, 9.97. X is equal to 93.718. Wow. Well then, that is definitely a lot. So now to find out how many grams of it, we need to know the constituents. So right now we have this amount of moles. So as you can see, that is intense amount of moles of it produced per how much given. But based on that Kc value, which is products of a reactant equilibrium value, that is what's going to be happened here. Hopefully I have it going the right way though. And then we go on to now find the constituents. So we have C, so that's 1C, 2S, okay? So that's carbon is 12.011, sulfur is 32.06. Let me just double check. Yep, that is correct. So that's 12.011, and that would be 64.12 plus 12.011. So in total, that's 76.131 grams per mole. Okay, so we're gonna have a very big number if everything we did was correct. It may not be the case, but based on that equilibrium constant, it seems like when we do this products over reactants, and because there is no based on this, I don't see any coefficients that we need as well. This is what we're going to have as x, which is quite a big number, but it's unfortunately nothing we can do about that. We have 76.131 grams per mole. Multiply that by the amount of moles we have, so that'd be times that 93.718, and we get the amount of grams in total is 7.1. How do I want to round this? Based on the amount of grams it gave us, 9.97. So 3 significant digits, 7.13 times 10 to the power of 3 grams. This is what I believe the answer should be. Let's see how we did. We have this, so just C over S, 9.4. Number of moles, per one, because they found the concentration. So that's what that was. I did not think about that at all. So it's going straight for the moles. So if we edited this, it'd be 9.4 over the concentration. So 6.5 liters was actually, so now we know it's going to be 9.97 moles in 6.5 liters, because we still need concentration. So this is a good example of why we have the brackets here, because it's concentration, not moles over moles. Okay, so because of that, we have 9.97 divided by 6.5. Our real concentration is 1.53, which is what, how do they get the number of moles per volume? It's 9.97. Where did they get the 10.9 from? Well, it looks like we both made a mistake then, because it should be 9.97 of S2. Well, interesting. So I guess we definitely have to solve this by hand, because we can't really compare anymore. So 9.4 is equal to then x over 1.53, which is a lot more reasonable. So 9.4 times, we might have getting the same answer though, because 1.53, because now this is the concentration. Concentration of this is going to be 14.418 per liter, but then we still have 6.5 liters, which still gives us back to our original amount of moles. Okay. This is 1.69. Oh, to reach, we did not do the ice table. That is what we were forgetting here, because we don't know if it's just a ratio like that. We have actually initial concentration equilibrium, okay, and the first amount was 9.97 moles. So we have, if this was S2 and this was CS2, we have 9.97 as the initial. CS2 would be 0, and then the change would be plus x, because it's only 1-to-1 ratio, minus x. It would be 9.97 minus x, and it would be just x. So Kc would equal to x over 9.97 minus x. Well, specifically, it wouldn't be 9.97. The concentration of this would be what we did earlier, 9.97 divided by 6.5, which was 1.53. So 1.53 minus x. So it'll be that times, that'll be 14.42 minus kcx is equal to x, and so we add the kcx to both sides, and the kc was 9.4, so that's 10.4x, because 9.4 plus just one more x is equal to 14.42. Divide both sides by 10.4, and we get x is equal to 1.386. So that's a much more reasonable x for sure. Okay. And because now we know the concentration of x, so it'll be 1.386 is how much was changed for the concentration. That's still moles per liter. Okay. But we still have 6.50 liters. So then that would be times 6.50. Let me see here. Okay, they got that. Okay. And yep, 6.5 times that answer, 9.01. We have 9.01 moles. And then because we did the conversion here, we have 9.01 times the 76.131, and so that means we have now 686 grams, which is perfect. So that should be our answer. And they got 750 grams. So this is incorrect, but this is simply because we have to show actually exactly how they got it, right? But right here they have, for some reason, 10.9 as the initial concentration instead of the 9.97. So 9.97 as initial concentration. So as you notice, if we had used that 10.9 that they gave us, we would actually end up with the same answer as them. So exactly like if we change that 10.9 divided by 6.5, we'd get 1.67, which is, well, 6.45, huh? A lot of things were different. So it seems like they had gotten numbers from some other area, not read the question completely, but it was important to figure out where we went wrong, because the answer should be 686 grams. So just as a review, to clear any confusion, we had first found out the concentration, okay, which then was used to we did a mini ice table, initial change equilibrium, to be able to find out the formula was going to be this, Kc is equal to x over 1.53 minus x, which is what they have here, okay. Then we did some rearranging, and then because of that we were able to actually solve for what the concentration of x would be, and this is what we got here, which is what they got something different, but that's how they were solving it. Then they found the moles by multiplying it by the liters, okay, and that's how they got the we got 9.01 and they got 9.87, and then we used that to multiply it by its molar mass, which is 76.131, which is what they did here, and that's how we got our 686, while they got 750. So I'm going to say 9.97 is the initial concentration, and volume was 6.5, not 6.7, 6.45. So with that being said, that's going to be our last question for tonight. Once again, thank you for joining me. I hope you have a wonderful rest of your evening. If you have any further questions, definitely check out the links in the description below. We're more than happy to help you. With that being said, have a wonderful holidays and see you next session.